Today we're going to talk about the combined gas law. The combined gas law is one of the laws that concern gases in chemistry that is based upon an ideal or the concept of an ideal gas. Now, what is an ideal gas? Well, the kinetic theory assumes that the particles of an ideal gas, first of all, have no volume, and that those particles are not attracted to each other. And an ideal gas is one that follows all of the conditions or follows the gas laws at all of the conditions of pressure and temperature. But we've got to keep one thing in mind, and that's that there's no such thing as an ideal gas. Okay, so that begs the question, if there's no such thing as an ideal gas, why are we bothering to learn these laws and use these laws to try to predict anything? Well, real gases behave a whole lot like ideal gases under most conditions of temperature and pressure, reasonable conditions of temperature and pressure. And you can make a lot of predictions about how gases are going to behave using the laws under those conditions. There are two major times or two major conditions where the gas laws break down. And those gas laws break down under conditions of low temperature and high pressure. When you get gases under those conditions, the gas laws really can't be used to predict much of anything. However, like I said, if you're dealing with reasonable conditions of temperature and pressure, like you're probably sitting in right now, then you can make great predictions with these gas laws. The combined gas law involves three, I guess you can call them minor laws, but there are three different laws that are put together for the combined gas law: Charles' law, Boyle's law, and Gay-Lussac's law. Charles' law, there's some ways that my students in the past have remembered the laws. This one is Charlie Brown is on TV. This has helped them in the past remember that Charles' law deals with T and V, temperature and volume. And this is a direct relationship. We say they're directly proportional because when the temperature goes up on a system, the volume goes up with that gas. If the temperature goes down, so does the volume. They're directly related because what one does, so does the other. A direct relationship. Now the next one, not my favorite way of remembering it, but it works. So boils have pus and volume. Pretty gross, but it's to help us remember that Boyle's law deals with P and V, pressure and volume. And using this one, I can also talk about the fact that the gross one, which I do think this is the gross one is the only one that is indirectly proportional or inversely related or inversely proportional. Meaning, if the volume goes up, the pressure goes down. If the volume goes down, the pressure goes up. So that helps us remember that the only inverse one, the only one that's opposite, is the gross one. So that's how we remember it. Gay-Lussac's law, we use guys like power tools. Now I'm saying that girls like power tools as well, but it doesn't work with our analogy. Guys like power tools. So this is to help us remember that Gay-Lussac's law deals with P and T, pressure and temperature. Just like Charles' law, this is a directly proportional relationship. So when temperature goes up, so does the pressure. When temperature goes down, the pressure does as well. So these are the three laws. Now you don't have to memorize the three equations that go with it. We don't have to memorize these separately from each other. What we can do is to use the combined gas law, P1V1 over T1 equals P2V2 over T2, and we can derive all of the other laws from this. And I'll show you how to do that in just a moment. First of all, as far as units are concerned, pressure can be in millimeters of mercury. It can be in atmospheres. It can be in torr or it can be in kilopascals. Doesn't matter as long as they're the same on both sides of the equation. Both pressure values have to be the same. If they're not, you have to convert one to the other. Volume, milliliters, liters. Honestly, volume could be in quarts, gallons, whatever, as long as it was the same on both sides of the equation. But we don't use those units really at all because we deal with the metric units, of course, in chemistry. Temperature is the one that's going to kick you in the teeth if you're not careful, because there is only one unit that it's possible to be used for any of the gas laws, and that's Kelvin. Kelvin temperature. Remember that to get Kelvin, we simply take Kelvin equal to Celsius plus 273. We just add 273 to the degrees Celsius, and that'll give us the Kelvin value. We have to use Kelvin because Kelvin has no negative values. Remember, Kelvin is based on absolute zero, and therefore there is no temperature lower than 0 kelvins. Since degrees Celsius can go negative, we could end up solving a problem where we had a negative volume, and that's just not possible. So keep that in mind. Now, when we solve these problems, remember how picky I am with how I want these set up. The first thing I want you to do is to label everything in the problem, and it is going to be required. It's 4 points, so make sure you do this. Find the unknown first. What are they asking you to find? It says here they're asking for the new volume of the gas. So we're looking for the new volume. Keeping in mind that the ones are the original or initial values. That N looked a little bit like an H. The original or initial values, and the 2's are the final values. Then if we want the new volume of the gas, we're looking for V2. So that's what we're looking for. The 5 liters then must be V1. Both 760 and 675 millimeters of mercury, those are pressure values, millimeters of mercury, and it's going from 760 to 675, so there's our P1 and P2 values. We've labeled everything, so let's go in and write our equation. P1 V1 over T1 equals P2 V2 over T2. We're looking for V2. And what variable is never mentioned? Nowhere in there does it mention a temperature value, so we can mark out temperatures, and we're left with P1 V1 equals P2 V2. Well, P and V, plus and volume, there's our pressure volume. That's Boyle's law, and I want you to put that up by the problem, because that's the one that we're going, I want you to label it right by the number on your problem, so that you'll start remembering whose law says what. All of this is designed to help you be able to recall this whenever it gets time to take the test. So now we're going to solve for V2, and notice I'm going to do this in green. You don't have to do this part, but in order to get V2 by itself, we're going to need to get rid of P2, which means we need to divide both sides by P2, which is going to reduce it to 1 and get rid of it on the V2 side, and it puts it on the bottom on the other side. So that leaves us with V2 being equal to, and there's one quick way to double check this. Make sure that whatever you've circled over here is what is on top on the other side. So if we circle volume, make sure volume's on top of on the other side, which it is. And then the rest of the P's and T's, they have to be on opposite sides of the division line. They cannot be side by side. We've got P1 over P2, so that's looking good. So just a quick visual double check to see if you've solved it correctly. So there's the equation, solve for V2. I must see that. Remember, it's not green, so it has to be there. Now we plug in values. V2 is going to be equal to P1, which is 760 millimeters of mercury, times V1, which is the 5.0 liters, divided by P2, which is our 675 millimeters of mercury. Millimeters of mercury cancel. I'm left with liters, which is a valid unit for volume. And I end up with V2 being equal to 5.629. Carry it out a few places. Remember, this time I'm not going to let you put it into scientific notation. You have to leave it in um, regular standard notation, but you still have to have sig figs. So it's going to be a little bit harder. Look back at our original sig figs. Looks like we have 3 sig figs here, 2 here, and 3 here. The lowest value is 2 sig figs. So I'm going to draw my sig fig line after 2 sig figs, and I come up with a value of 5.6 liters for the volume. Second problem, we're going to do the same thing that we just did. Want everything labeled. It says it's looking for the original temperature, and the original temperature would be our T1 value. So the 250 degrees up here must be T2. Now, my opinion is as soon as you see a temperature right beside it, you should write plus 273, so you won't forget to do that in the problem. Or you will, both on the worksheet and the test, so be careful with that. It's in green, so you don't have to. Just a word to the wise. So going from 0.250 liters to 1.20 liters looks like that's going to make this a V1 and the 1.20 liters a V2. So writing our equation, P1 V1 over T1 equals P2 V2 over T2. We're solving for V2. And it looks like on this one that pressure is never mentioned. So pressure is going to be able to be marked out. We're left with V1 over T1 equals V2 over T2. This is our TV1. Charlie Brown is on TV. So this is Charles' law. So make sure and write that up beside the number on the problem. And now, the bane of existence for pre-AP and AP students everywhere, solving for a bottom variable. I just circled V2, didn't I? I did not mean to up there, so I'm going to erase that circle off, rewrite that a little bit. That was probably a bit confusing when I did it that first time, but hopefully you realize now we're supposed to be solving for T1. That's still going to be marking out our pressure values. So again, we're solving for a bottom variable, T1, not V2, T1. So the first thing I've got to do is to get T1 on top. So I'm going to multiply both sides by T1. I'm going to reduce it to 1 over here. So now I'm still solving for T1. It's on top now, but now I've got to get it by itself. So I've got to get rid of V2 and T2. Now I'm not going to go through multiplying on both sides and dividing on both sides for all of these. I'm going to do a bit of a shortcut. If V2 is on this side, yes, I'm going to be dividing both sides by it, but all I'm going to think in my head is, okay, I can move this V2 and get rid of it over here, but since it's on top on this side, I've got to put it on bottom on the other side. For T2, I can get rid of T2 on this side, but since it's on the bottom here, I must move it to the top on the other side. Just a bit of a shortcut. We still divided both sides by V2 and multiplied both sides by T2, but it was just a little bit less writing to get in the way and cause confusion. So T1 ends up being V1 times T2 over V2. And it doesn't matter which side the T and the V are on, as long as they're both on top. Multiplies out 2 times 3 is the same as 3 times 2, so it won't matter. But now we plug and chug. T1 is equal to V1, which is 0.250 liters, times T2. Add that 273, and we get 523 kelvins. And then V2 is on the bottom. That's our 1.20 liters. Liters will cancel. Left with kelvins, which is a valid unit for temperature. So it looks like we did a good job. We end up with T1 being equal to 108 point, I believe, 95. But looking back at original sig figs, looks like we've got 2 sig figs here, 3 here, and 3 here. Looks like we want 2 in our answer. So draw our sig fig line. Now this one is a little bit harder. This says that we're supposed to round up, so we do that and we come up with 11. 1, 1. And I have so many people that leave it there. But remember, can we leave out or leave blank a whole number place value? And the answer is no, we cannot. So since we rounded up there, that leaves this at a 0. So this becomes 110 kelvins. Now, if we wanted to change that to Celsius, we would simply subtract 273, but it didn't ask us for Celsius. And the AP rule is if they don't ask, don't go that step further. We could do a stupid mistake just rushing through and do all the hard stuff correctly, and at the end, add 273 instead of subtract it and get the problem wrong. So just leave it like that. The last one that we're going to cover in this set of notes deals with a gas left in a used aerosol can that's at a 1.25 atmosphere pressure at room temperature. If you throw it into the fire, what's the pressure going to be when the temperature reaches 927 degrees Celsius? It's kind of a life lesson here too. Looks like it's asking us for the final pressure, so we're looking for P2. So evidently the 1.25 atmospheres is P1. The 27 degrees Celsius is T1. Now remember, that's going to be plus 273 at the end, and the 927 is going to be plus 273 as well, and that's going to be our T2. So now we write our equation, P1V1 over T1 equals P2V2 over T2. I'll get this hopefully right this time. We're solving this time for our P2. So we're solving for P2. What does it never mention? Never mentions volume. So we can X those out. So whose law is it that deals with P and T? Power tools. That's guys like power tools. Gay-Lussac. So now we're going to solve for P2, and all we need to do to solve for P2 is simply get rid of the T2. Remember, it's on bottom on this side, so we can move it to the top of the other side. And we end up with the equation that P2 is equal to T2 times P1 over T1. P is on top. That's what we're trying to solve for. And the T's are not side by side, so that looks like we've got a good equation. Plug and chug. P2 is equal to T2. Looks like T2 is going to be 1200 kelvins when we add that 273. P1 is 1.25 atmospheres. T1 is 27 degrees. Add the 273 and we get 300 kelvins. Kelvins cancel, left with atmospheres. When we multiply this out, we get that P2 is equal to 5, even. We look back up at our original sig figs, and looks like 27 up here is going to be our limiting factor to 2 sig figs. And to get this value to 2 sig figs, looks like we're going to need to add a 0.0 onto it. And that's going to be atmosphere. So notice that we kicked that up to about 5 times the pressure by heating it up. So the chances of that can being able to withstand that increase in pressure are very slim. So again, life lesson. So those are Boyle's law, Charles' law, and Gay-Lussac's law. In the next set of notes, we'll look at what happens when we combine all of those variables into the combined gas law.